The invisible skeleton of the universe, dark matter, and the cosmic horizon. Imagine staring into the darkness, seeing nothing, yet knowing that beneath this black canvas, halos of unseen matter still stretch across the void. Though they no longer host shining stars, these structures continue to bend space, influence the paths of objects, and define the architecture of the cosmos. The vast cosmic web, once illuminated by galaxies threading along its filaments, will endure as a ghostly network of the invisible dot. In such a time, the role of dark matter becomes even more fascinating. In a universe expanding under the push of dark energy, dark matter acts as the counterforce. It is the portion that resists dispersal, holding together through gravity. Even as galaxies drift apart, each remains enveloped in its invisible cocoon of dark matter. This means that while the universe's grandest structures fade from view, smaller systems can remain bound for far longer. Clusters of collapsed stars, black holes, or even rogue planets could continue orbiting within a halo of dark matter, holding on to one another for countless ages. Isolated islands of structure, amidst oceans of nothingness. But what of dark matter itself? Will it endure forever? Some scientists wonder whether dark matter might decay over extraordinarily long times. If it can, even the universe's invisible skeleton could eventually crumble. Yet no evidence for such decay exists. As far as we know, dark matter has remained constant since the dawn of time, and there is little reason to expect its disappearance anytime soon. If it persists indefinitely, the final universe will not be entirely empty. Deep within, this strange, invisible substance will continue to stretch a faint shadow of the young cosmos. There will be no light, no heat, no stars to behold, yet gravity will still move objects. Invisible halos will continue to guide the paths of the last remnants. Black holes drifting through space, rogue planets wandering forever, clouds of dust adrift in the void without dark matter. These remnants might disperse more rapidly. With it, however, structure endures. Even in the deepest silence of time, the cosmic graveyard will not be utterly flat. Its faint framework, like the arches of a cathedral stripped of roof, stained glass, and candles, remains. Dark matter is like those arches, a form that survives after the light has gone, shaping the void. Walking among it would be traversing a world where everything is hidden, where the skeleton of creation is all that remains. There is even the strange possibility that dark matter could serve as the ultimate foundation for life or intelligence in the distant future. In a universe depleted of energy, could unimaginable life forms learn to utilize dark matter itself? This is far beyond our current understanding, but history reminds us how often life surprises us. Just as the earliest microbes thrived on chemical energy in rocks, long before plants and animals existed, perhaps the distant future could harbor organisms feeding on forms of matter that seem non-existent to us. If so, dark matter would not merely be the universe's skeleton, it could become its final reservoir of hidden possibilities. For now, all we can do is wonder. Dark matter is invisible to our eyes and instruments, yet its significance cannot be overstated. It is the silent architect of galaxies, the hidden thread of the cosmic web, and possibly the last survivor when all else has vanished. When the rest of the universe is gone, the future may seem cold and silent, but perhaps invisible is a better term. Dark matter will still be there, sustaining a cosmos that appears empty to us. Beyond the observable universe stretches a realm we can never witness. Our observable bubble has a finite radius. Beyond it lies an expanse forever hidden from us. Even the most powerful telescopes, even billions of years of patient observation, cannot pierce this horizon. Yet beyond it, the universe continues. Galaxies, clusters, and cosmic structures live, age, and die, eternally hidden from human eyes. We know the universe is expanding, yet we cannot access its full contents. Over time, as cosmic expansion accelerates under dark energy, more and more galaxies slip beyond our horizon. Once gone, their light will never reach us, disappearing forever from view. From our perspective, the universe seems to be erasing itself. Galaxies once filled with stars, star-forming regions, and supermassive black holes may be among the richest regions. Yet ultimately, they will share the fate of the observable universe. Stars will burn through their fuel. Supernova will scatter elements across space. Black holes will eventually evaporate over inconceivable timescales. Without new sources of energy, these distant galaxies will fade into silence. The tragedy is magnified by our inability to witness their final acts. They are lost to us, separated not just by distance but by the laws of physics. The universe we observe may be far older and stranger than we realize. Regions beyond our horizon might evolve differently, hosting cosmic events we cannot even imagine. Entire epochs of star formation, galactic collisions, and stellar deaths may continue beyond reach, leaving behind only cold remnants. Some clusters may burn out faster, leaving only lifeless relics. They exist beyond our comprehension. Accelerated cosmic expansion deepens this isolation. In the far future, even the galaxies we see today will fade into invisibility. Only our local group of galaxies might remain in view. Everything else slips beyond the horizon, trapped in dark and lonely voids. Billions or trillions of years from now, future observers will inhabit a universe that seems far smaller than ours. Their cosmic graveyards not only unseen but unknowable, and yet, beyond the horizon, galaxies are not just disappearing, they are still being born. We cannot see them, but they must exist. New stars ignite, new planets form, new possibilities arise. If life exists in these inaccessible realms, it evolves under skies we can never know. Just as we remain unaware, entire civilizations may rise and fall in isolation, trapped in their cosmic bubbles, separated forever by the expansion of space. This gives the universe a strange duality, immense beyond comprehension, yet confined by the limits of observation. No matter how advanced a civilization becomes, no telescope or technology can pierce the veil beyond the observable universe. The speed of light is not merely a challenge, it is a fundamental barrier. Some mysteries are thus permanent. The invisible graveyards of distant galaxies remain hidden, not because we lack the instruments, but because the universe itself forbids access. Yet our minds reach outward. Scientists extrapolate beyond the observable bubble, using the patterns of structure, galaxy distribution, and the laws of physics to infer that the unseen universe must look much like the seen. Yet this remains an assumption. Surprises may exist, matter arranged differently, expansion manifesting uniquely, or forces we have yet to discover. The graveyards of those galaxies may follow timelines completely unlike our own. Perhaps the universe's true death has already occurred in regions we can never reach. Stars may be gone, black holes evaporated, vast regions already cooled and lifeless. If so, the end of everything is not a distant possibility, but a present reality advancing from the hidden corners of the cosmos. In this case, the observable universe becomes a shrinking island of light amid dark ruins. These cosmic graveyards remind us that time passes, that stories conclude, and that meaning is shaped by finality. Even invisible galaxies tell us that the universe is not infinite in its persistence. Loss exists even in the vastness, hidden though it may be. The thermal death of the universe is a cosmic funeral. In unimaginably distant times, beyond the lifespan of stars, beyond the collapse of galaxies, beyond the evaporation of the last black holes, the final chapter awaits. Unlike violent supernova or collapsing stars, this end comes quietly, gradually, and inevitably. It is not a single event, but the sum of countless processes fading over unimaginable timescales until the universe loses its capacity for change. To envision it, we must imagine periods so vast that even trillions of years become mere steps toward a greater void. The concept begins with the second law of thermodynamics. At its core, this law tells us that energy naturally disperses, transforming from dense, useful forms into more widespread, unusable forms. Today's universe shines because stars are hot, dense furnaces surrounded by the cold vacuum of space. This contrast between hot and cold drives energy flow, enabling stars to burn, planets to orbit, and life to exist. But over time, as stars die and energy reservoirs are depleted, these contrasts diminish. Energy spreads more evenly across space. Without contrast, nothing moves, nothing shines, nothing lives. In the deep future, we can see this unfolding. Stars like our sun exhaust their fuel and fade. Galaxies continue to glow for a time with the light of younger stars, but billions of years later, all reaches its end. Star formation slows, then stops. Spiral arms once bright, with energy dimmed to shadows. White dwarfs cool to faint embers. Neutron stars become silent spheres. And black holes, though seemingly eternal, evaporate via Hawking radiation over timescales that dwarf any star's lifespan. As these structures fade, the universe softens. Energy, once clustered in stars and galaxies, spreads more evenly. With no new concentrated sources, there is nothing left to rekindle creation. Galaxies empty, space darkens, and silence deepens. The universe enters a dark age, leaving only faint traces of radiation, scattered particles, and the ever-expanding void. Expansion itself contributes to this decline. Each era, galaxy, resurrection of stars, and the role of rogue planets is akin to the rebirth of a star. Hawking radiation suggests that black holes might evaporate over inconceivably long times, yet in their final moments, as they shrink into nothingness, they could release intense bursts of energy. For distant observers in the far future, this might appear as the final flare of a long-dead star. It is not true resurrection, but an echo of the last heartbeat of something defying death across eons. More speculative ideas, still unproven but keeping debate alive, have also been proposed. Some physicists suggest that under certain exotic conditions, dead stars could capture enough gas or dark matter from their surroundings to reignite nuclear fusion in their cores. If possible, a star could flare to life again after billions of years of silence. Such events, if they occur at all, would be extraordinarily rare, and we might never witness one. Yet, in an infinite cosmos, even the rarest occurrences may find a stage. The line between life and death in the universe is never absolute. When stars exhaust their fuel, they do not vanish entirely. They leave remnants that can interact, flare, or even explode under the right conditions. A gas-stealing white dwarf, a reawakened neutron star. A black hole drawing its last breath each represents, at least temporarily, a form of resurrection. The universe is full of objects that, though technically dead, find ways to stir, shine, and even intimidate. Death in the cosmos, like life, is often more complex than it first appears. Even in the cold graveyards of galaxies where stars should lie silently, echoes of light, vibrations of energy, and whispers of revival may persist. The role of rogue planets in a dying universe. When stars die, their planets often face destruction. Some are swallowed as their stars expand. Others freeze in darkness once their sun Yet not all planets remain bound to their systems forever. Some are set free, ejected by the chaotic dance of gravity or by stellar collisions, deaths, or explosions. These lone wanderers are called rogue planets, worlds without a sun, drifting without a fixed source of light or heat. Rogue planets are nearly impossible to detect against the black backdrop of space, remaining hidden, dim, and intriguingly mysterious. However, when imagining the far future of a universe where stars have long vanished, rogue planets may assume a new significance. In an otherwise silent cosmos, they may be the final survivors, carrying traces of complexity even as everything else fades. During a galaxy's youth, as stars and planets form, gravity is both constructive and destructive. Young stars often form in clusters, pulling on each other and disturbing the orbits of newborn planets. A close encounter with another star can eject a planet from its system entirely. The planet does not disintegrate, it continues its journey, traveling through space indefinitely. As cosmic history advances and stars age and destabilize, they may also eject their planets. An expanding red giant can disrupt orbits, while a supernova may scatter an entire system into darkness. Through these and other processes, countless planets are liberated, becoming travelers in the cosmic wilderness. Some estimates suggest there may be more rogue planets than stars in our own galaxy, billions drifting silently. Throughout their existence, rogue planets remain cold, dark, and nearly invisible. Without a star to provide heat, their surfaces plunge into deep freeze. They may seem like lifeless rocks or aimlessly wandering frozen gas giants, yet secrets could lie beneath icy shells. A planet with a thick atmosphere may trap some heat, while a massive planet with internal radioactive decay may retain warmth in its depths. Most intriguing are rogue planets harboring subsurface oceans beneath kilometers of ice. Shielded from the vacuum of space. On Earth, life can exist without sunlight, thriving instead around hydrothermal vents powered by the planet's own heat. A similar scenario could exist on rogue planets, meaning these dark worlds may not be entirely barren. In a universe where stars have long gone, secret refuges of life might persist. Imagine a time, 10 trillion years hence, when galaxies are so distant from one another that light from one cannot reach another. By then, most stars will have perished, even the longest-lived, dimmest stars consuming their remaining fuel. Only white dwarfs, neutron stars, and black holes will remain from stellar systems. Yet the rogue planets once set free will endure. Unlike stars, they do not require fusion or radiation to survive. They are still long-lived, resilient, the remnants of an old universe, drifting forever as the cosmic stage cools in Kirkinans. In a far future universe, once home to trillions of suns, only scattered embers and rogue planets may remain. These planets are not merely survivors of stellar death, they are survivors of cosmic death itself. Their significance lies not only in endurance but also in what they might carry. A rogue world could harbor chemical complexity, or even life long after stars have disappeared. Civilizations, if they still exist, could find refuge on such worlds. Advanced beings might carve into a rogue planet's crust, harnessing geothermal energy to create artificial warmth, sheltering themselves beneath thick ice from cosmic rays and the vacuum of space. Such existence would be far removed from the bright, open worlds we imagine today. Yet surviving in a dying universe may mean adapting to cold and darkness. Rogue planets could be among the last possible homes. Rogue planets may also play another role. As galaxies age and stars fade, gravitational interactions among remnants continue. A rogue planet could be recaptured, drawn into the orbit of a stellar remnant or even a black hole, becoming part of a new system spinning through endless night. Such captures would be rare in the vast emptiness of space. But rogue planets could still participate in the final dance of cosmic matter. Even in the era of gravitational decay, they weave new patterns. In the distant future, as black holes evaporate and the last traces of starlight vanish, rogue planets will continue their journeys. Of course, they are not indestructible. Given enough time, their atoms may decay according to the laws of physics. Yet across timescales beyond comprehension, trillions of years, they will outlast the stars that once gave them life. In the silence of the far future, a rogue planet may drift alone, carrying the memory of a universe that once shone brightly. If life can find a way, rogue planets, if life clings to them, represent not only the last physical survivors but also the last bearers of life itself. They are both tombstones and arcs, proving that the cosmos, however bleak, has not lost all its complexity at once. Instead, it slowly fades, leaving dispersed worlds adrift in darkness. The story of rogue planets is a tale of endurance, the survival of fragments of creation outlasting their creators. In the infinite night of a universe approaching heat death, they may carry the final sparks of forgotten ages. Dark matter and the invisible graveyard. Dark matter has always been a silent player in the story of the cosmos. Unlike stars dying in dramatic flares or galaxies raging with billions of suns, dark matter does not shine, emit heat, or interact with light, yet it holds the cosmos together, scaffolding the formation and sustenance of galaxies. Without it, the universe's familiar structures could never have formed. And long after the last stars fade, dark matter will remain, an invisible framework extending into the cosmic graveyard. In the early universe, dark matter shaped the first galaxies, forming invisible wells that drew ordinary matter inward. Over time, stars ignited within these wells, and galaxies were born. But when these galaxies eventually exhaust their fuel and their stars burn out, dark matter remains. It does not die or decay like ordinary matter. Its existence continues silently and subtly, quietly guiding the motion of everything left behind. If the universe becomes a cold expanse of dim remnants, with black dwarfs, neutron stars, black holes, and nothing else, dark matter will persist binding them, spreading through voids, and connecting them in invisible networks. Scientists still do not know what dark matter truly is. It might be a particle unlike anything detected, or something stranger, a field or effect barely comprehensible. What matters for the story of the distant future is its sheer persistence. Stars may burn out, galaxies may drift apart, even black holes may evaporate over unimaginable times, yet dark matter endures indefinitely. If it persists, it will form the universe's last great structure, framing the cosmos when energy and light are gone. The fate of life and the cosmic cycle of stars and black holes' life would meet its end in those days. Without new stars forming and without fresh energy to sustain ecosystems, galactic environments become inhospitable to growth. In such graveyards, the chances for life to continue or even to thrive dwindle to near nothing. The destiny of habitable planets seems bound to the inevitable decay of the cosmos. Each planet is granted a temporary window of habitability, dictated by the lifespan of its star and the changing conditions of its galaxy. For Earth, this window extends roughly another 5 billion years until the Sun swells into a red giant. 4 planets orbiting massive stars. It might last only a few million years, a blink of an eye. On cosmic timescales, even planets around long-lived stars eventually face decline as their suns age. Stars expand and leave behind only remnants. Yet, in the universe there is a peculiar continuity. When stars die and planets freeze, the matter that once supported life does not vanish. Carbon, oxygen, and nitrogen, the building blocks of biology, remain scattered across the galaxy. They may become trapped inside cold white dwarfs, locked within planetary crusts, or drift as dust between stars. Even if it takes trillions of years for these cycles to unfold, the elements continue to play a role in future cosmic cycles. Galactic and stellar graveyards are not empty. They are repositories of the raw materials for new worlds, and perhaps, in a distant future, for new forms of life. What about black holes? Will they evaporate, or will they consume the universe? Black holes feel like eternal traps, swallowing everything that comes too close, never giving it back. For much of modern astronomy, they were considered the universe's ultimate endpoints, objects that devour without return. But in the 1970s, a surprising idea shook this perception. Stephen Hawking proposed that black holes are not completely black. Instead, they emit a faint glow, a slow leak of energy. This suggests that even these gravitational monsters might one day disappear. Known as Hawking radiation, this concept has forever changed our understanding of black holes' fate. By extension, the long-term future of the cosmos. To grasp why, we must consider how the universe behaves on its tiniest scales. In the world of quantum physics, empty space is not truly empty. It seethes with so-called virtual particles, pairs of matter and antimatter that constantly appear and vanish. Normally, these pairs annihilate almost instantly, leaving no trace. But near the edge of a black hole, close to the event horizon, something different can happen. One particle may fall into the black hole while its partner escapes. To an outside observer, it appears as if the black hole is radiating. And since energy must come from somewhere, the black hole loses a tiny fraction of its mass. The process is incredibly slow. For a black hole the size of our Sun, complete evaporation would take about 1,067 years, a number so vast it is almost unimaginable. 4 supermassive black holes at the centers of galaxies. The timeline stretches to 10,100 years or more, far exceeding the current age of the universe by an inconceivable margin. For now, black holes seem eternal. Yet, over unimaginable spans of time, even they may vanish. Evaporation begins subtly, almost imperceptibly. For billions of years, a black hole appears stable, its gravity unchanged. But over inconceivably long durations, as it shrinks, its emitted radiation intensifies. The black hole slowly heats up, shining ever brighter, until in its final moments it releases a tremendous burst of energy. A black hole that once swallowed stars ends its life in a brief but brilliant flare, completely evaporating in a final explosion of light and heat. If this picture is accurate, the universe's most powerful engines are not eternal prisons but transient features. In the farthest conceivable future, no black holes will remain. The cosmos will be filled only with faint radiation, cooling and expanding forever, a universe not just silenced but stripped of even its darkest shadows. Yet not everyone is certain this will happen. Hawking radiation has never been observed directly. Its effect is too weak to detect with current technology. Our best evidence comes from the mathematics of quantum theory and general relativity, to robust yet not fully reconciled frameworks. Some physicists suspect we may still be missing a piece of the puzzle. Perhaps black holes do not evaporate entirely. Perhaps they leave behind small, stable remnants carrying traces of their existence. Or perhaps our understanding of gravity itself will evolve, altering this story. Another possibility is that black holes may play an active role in the universe's distant future. Instead of fading, they could continue to dominate the cosmos long after stars have burned out. As galaxies die and stellar remnants drift apart, black holes may remain the last strongholds of matter. Rogue stars could be drawn to them. Planets or even other black holes could gradually merge into ever larger structures. From this perspective, black holes may not quietly disappear but continue to reshape the universe toward its dark, distant future. Imagine a time trillions of years hence, when all stars have faded and galaxies have dispersed into scattered matter. Black holes lie in wait, swallowing anything that comes too close. Entire solar systems could vanish into their depths. Even if evaporation eventually triumphs, the universe might belong to black holes for an astonishingly long period of cosmic history. Which scenario is more likely? Will black holes ultimately evaporate and leave the cosmos empty? Or will they persist, consuming stray matter and ruling the universe indefinitely? The truth may hinge on aspects of physics we do not yet understand. Hawking radiation bridges two great, often incompatible theories. To fully answer the fate of black holes, we may need a deeper theory of everything uniting the very small and the very large. If black holes evaporate, the universe seems destined for a slow, complete disappearance, leaving no structures behind. If they persist, the cosmos may remain shaped by their presence for far longer, with giant black holes standing as monuments to creation's final acts. In either case, the timescales are so immense that our own era of stars and galaxies is but a brief spark compared to what lies ahead. Cosmic zombies. The potential for stellar resurrection. A star consumes its fuel, becomes a red giant, collapses, explodes, or fades to a dim ember. The story seems complete, a chapter closed forever. Yet exceptions and strange events exist. Under certain conditions, dead or dying stars can experience a kind of revival. The most familiar example comes from white dwarfs in binary systems. A white dwarf orbiting a living companion star may appear invisible, quietly circling, but as the companion evolves and expands, gas from its outer layers can flow onto the white dwarf. This fresh hydrogen accumulates on the surface until it ignites in a sudden nuclear explosion. The dwarf flares, producing what astronomers call a nova. To an observer, the dead star seems awakened, glowing with newly found energy. It has not truly returned to youthful vitality, but the dramatic flare makes it appear resurrected. These nova events can repeat as long as the white dwarf continues, siphoning fuel from its companion. Even more dramatic is when the white dwarf accumulates too much matter, surpassing a critical mass. It can no longer support its own weight, collapsing and exploding as a supernova, leaving only dispersed remnants behind. This is less a resurrection than a final catastrophic blaze. Yet even dead stars occasionally find a way to shine spectacularly once more, if only briefly. Neutron stars can also behave like cosmic zombies. For millions of years, they may spin silently, their magnetic fields weakening and energy gradually leaking into space. Then, triggered by unknown forces, they can suddenly come alive. Magnetars, a special class of neutron stars, are famous for this, emitting bursts of radiation powerful enough to outshine entire galaxies for moments. Stars thought long extinguished awaken suddenly, their flares still mysterious but often attributed to twisting magnetic fields, releasing immense stored energy. Some neutron stars even emit impulses, turning on and off over years or decades, as if waking from a deep slumber. Sometimes the most dramatic resurrections occur when a neutron star merges with another neutron star or a black hole. These collisions unleash colossal forces, scattering matter and producing energy bursts visible across billions of light-years. Gravitational waves ripple through space-time itself, and heavy elements are forged. In a sense, the death of one object gives rise to creation new elements, new matter. Some astronomers even speculate that black holes themselves might one day release energy or particles, continuing the cosmic cycle. Life in a galactic graveyard. Is the universe too harsh for complex life? Planets and galaxies like our own appear as cradles of life, brimming with energy and material for growth. But when we turn our gaze to the older, quieter regions of the cosmos, the galactic graveyards, the picture shifts. Here, the universe reveals a harsher face. Galaxies that once shone brightly with stars have become dim, silent assemblies of ancient suns. The gas and dust required to forge new stars and planets have thinned or vanished. Instead of landscapes of birth and growth, we find realms of endings and survival under extreme conditions. Can life, especially complex life, truly exist in such an environment? In their youth, galaxies are rich in gas and dust, the raw materials for stars, planets, and the heavy elements essential for life. Carbon, oxygen, nitrogen, phosphorus, and other elements are forged in stellar cores and dispersed into space when stars die. In a young galaxy, the continuous cycle of star birth and death provides a replenishing source of chemistry necessary for life. In a galactic graveyard, however, this cycle slows and eventually halts. Fewer new stars mean fewer supernovae to enrich the galaxy with heavy elements. Over time, fresh material dwindles, locked away in old stars or dispersed too thinly to form new worlds. This scarcity of resources presents a serious obstacle for life, particularly for complex organisms that require stable planetary conditions. Even planets that formed earlier in the galaxy face another challenge. Aging parent stars. In old galaxies, surviving stars are typically smaller, dim red dwarfs or bloated, unstable giants approaching the ends of their lives. Red dwarfs may burn for trillions of years but are often inhospitable, emitting intense radiation that can strip atmospheres or sterilize planetary surfaces. Giant stars provide brief warmth but are doomed to unstable deaths, shedding their outer layers and leaving behind dense, white dwarfs. Planets orbiting such stars might survive physically, but their environments change so dramatically that sustaining life becomes nearly impossible. A stable sunlight, a prerequisite for complex life, is rare in these stellar graveyards. Radiation adds another layer of danger. In active parts of the universe, galaxies are filled with energy, much of it balanced by ongoing star formation and protective magnetic fields. In dead or dying galaxies, conditions differ drastically. Supermassive black holes often remain at their centers. Even if the galaxy is quiet, the black hole may erupt, sending streams of high-energy particles and radiation into surrounding regions, sterilizing potential habitats. Without the constant turbulence of young stars and gas clouds to absorb and distribute this energy, the galaxy becomes an even harsher environment for fragile biospheres. The chemical balance of the universe also shifts with age. Early galaxies are typically metal-rich. Astronomers use metals to describe all elements heavier than hydrogen and helium. Over time, star formation enriches galaxies with metals, creating conditions suitable for rocky planets like Earth. But in dead galaxies, ongoing star formation ceases, and this enrichment halts. Over trillions of years, stars burn out their remnants, and galactic chemistry stagnates. The number of planets rich in life-essential elements steadily declines. If life emerged in such a galaxy, it would face the challenge of survival in an environment where the building blocks are no longer replenished. Some argue that simple, resilient microbial life could persist. On Earth, microbes thrive in boiling deep-sea vents, frozen Antarctic deserts, and even radioactive waste, demonstrating extraordinary resilience. Similar life forms might survive in hidden subsurface oceans of planets or moons orbiting aging stars. However, when considering complex life capable of ecosystems, intelligence, and civilizations, the odds diminish sharply. Complex life requires not only survival but long-term stability, a stable climate, steady energy sources, and protection from catastrophic radiation. These qualities are often absent in galactic graveyards. Perhaps the universe itself imposes natural limits on how far life can advance. The very conditions that allow galaxies to form and evolve may also guarantee that they eventually become inhospitable. A galaxy may offer a golden age for life to emerge and flourish, but this period is temporary. As the galaxy depletes its fuel, the window for complex life narrows and ultimately closes. This perspective may help explain why we have yet to detect alien civilizations. Perhaps galaxies are only as long-lived as their active phases. By the time we search, the stars that once nurtured life may have long since gone dark. On Earth, the emergence of complex organisms took billions of years, and intelligence even longer. Had we been placed in a galaxy already on the road to stellar death, there may not have been enough time for us to arise, before stars faded and resources ran out. This suggests that the emergence of complex life depends not only on the right type of planet and star, but also on the right moment in cosmic history. Too early, and the galaxy lacks heavy elements needed to form Earth-like worlds. Too late, and the galaxy has exhausted its fuel, leaving little room for growth. The result is a sobering picture. The universe may be teeming with planets, but many orbit stars in quiet, ancient regions, worlds where, from our perspective, the likelihood of anything beyond resilient microbes is low. The grand narrative of life may not be written evenly across the cosmos. The rise of complexity may depend on narrow windows within a galaxy's life. Outside these windows, the universe is simply too harsh, too unstable, and too resource-poor to support advanced life. Billions of years from now, our galaxy may also fall silent, once its gas reserves are depleted or expelled. The bright bands of stars that light up our night sky could fade, leaving only the faint, lingering glow of ancient stars. In this sense, dead disk galaxies are more than remnants. They are warnings of what the future may hold. Interestingly, not all of these galaxies are entirely uniform in their silence. Some harbor small pockets of lingering star formation, teeny flickers of activity in an otherwise darkened expanse. They serve as subtle reminders that life and death in the cosmos are rarely absolute. The balance between activity and dormancy is delicate, and galaxies can linger in these transitional states for billions of years. Modern telescopes have been instrumental in uncovering these galactic fossils. The Hubble Space Telescope captured detailed images of these faint, fading spiral arms, revealing forms that, without spectral analysis, could be mistaken for active galaxies. More recently, the James Webb Space Telescope, with its infrared capabilities, has begun to probe the stellar populations of these silent systems, helping astronomers determine when star formation ceased and tracing the slow death of galaxies over cosmic time. Some dead disk galaxies appear to have shut down surprisingly early in the universe's history. This suggests that galaxies could live full, active lives and yet fade away long before the cosmos reaches its current age. Such findings are reshaping our understanding of galactic lifespans and emphasize the critical role of environment, random encounters, and cosmic feedback in shaping the fate of stellar worlds. Beyond their scientific value, dead disk galaxies capture the imagination. They remind us that even the grandest structures can fall silent, revealing the fragility of cosmic activity. While their stars no longer renew, they continue to shine for billions of years, carrying the memory of brighter times as they drift quietly through space. The story of these galaxies is part of the broader narrative of cosmic aging. Just as stars have lifespans, so do galaxies. The death of star formation in their disks is a step toward a cooler, quieter universe. A supernova explosion is not just a spectacular end for a massive star, it also leaves a lasting imprint on the surrounding cosmos. The energy released in the explosion is sufficient to forge elements heavier than iron, which are then scattered into space, enriching the interstellar medium. Without supernova, the universe would lack many of the elements essential for forming planets and life as we know it. Today, supernova act as cosmic furnaces, generating the elements needed for planets and everything else in the universe. Their shockwaves can also trigger the birth of new stars by compressing nearby gas clouds, causing them to collapse and ignite new stellar formation. In this way, the death of one generation of stars sets the stage for the next, maintaining a continuous cycle of creation. Supernova, therefore, are not just endpoints, they are vital steps in the ongoing cycle of stellar evolution and galactic growth. Galaxies themselves, like stars, are not eternal. They are massive assemblies of stars, gas, dust, and dark matter bound together by gravity, each following its own life cycle. Observing galaxies scattered across the universe, we see not only islands of stars but also vast evolving structures that grow, collide, and eventually fade away. Their stories, unfolding over billions of years, shape the very framework of the cosmos. Galaxies began forming long after the Big Bang, when slight fluctuations in the nearly uniform distribution of matter allowed regions to attract more material under gravity. These dense pockets gradually accumulated enough gas to form stars, giving rise to the universe's first galaxies. These early galaxies were small, irregular, and filled with hot, rapidly burning young stars. A far cry from the grand spiral structures we observe today, but they planted the seeds for the future. As galaxies aged, they evolved in both form and behavior. Gas clouds collapsed to create new stars, while dying stars recycled material back into the galactic environment. Supernova enriched galaxies with heavy elements, providing the raw ingredients for planets, moons, and other celestial bodies. Over billions of years, this cycle of stellar birth and death shaped the evolution, chemistry, and appearance of galaxies. Young galaxies were chaotic places, alive with rapid star formation. Over time, many stabilized into more orderly structures, like the spirals we can observe nearby. Yet, not all galaxies followed the same path. Some, like the Milky Way, developed prominent spiral arms extending from a central bulge, achieving a relatively stable structure. Others became massive elliptical galaxies, lacking clear spiral patterns and often dominated by older stars with little ongoing star formation. Irregular galaxies, by contrast, resisted neat classification, often shaped by gravitational interactions and collisions with neighboring systems. Collisions and mergers play a central role in galactic evolution. While stars within galaxies are spaced too far apart to collide directly, entire galaxies can end frequently. Gravity pulls them together across vast distances, and when they meet, their stars, gas, and dark matter swirl and intermingle, reshaping their structures. In some cases, the spiral galaxies merge into a single elliptical, losing their intricate forms. In others, colliding gas clouds trigger bursts of star formation. These cosmic dances unfold over hundreds of millions of years, gradually transforming the universe's landscape. The Milky Way itself has grown through countless mergers and the assimilation of smaller galaxies. Evidence of past collisions remains visible in streams of stars and remnants of absorbed galaxies. In the distant future, the Milky Way will collide with its nearest large neighbor, the Andromeda Galaxy. In roughly 4 billion years, the two galaxies will begin merging, forming a new, larger galaxy. While most stars will avoid direct collisions, the galaxy's shapes will be reshaped and rebuilt. A galaxy's life also depends on its fuel. Stars form from cold gas, and without it, new stars cannot emerge. Over time, galaxies consume or lose their gas through star formation or powerful outflows driven by supernova and central black holes. When a galaxy exhausts its star-forming gas, it quiets down, producing few new stars and aging into a population of older, redder stars. Such galaxies are often called red and dead, indicating that their active growth days are over. Supermassive black holes at galactic centers add another layer to this story. Nearly every large galaxy harbors a central black hole, millions or even billions of times the sun's mass. When actively accreting gas, these black holes can influence the entire galaxy, releasing immense energy that can heat surrounding gas and suppress new star formation. Over time, this can starve a galaxy from within, contributing to its quiet, aging state. Galaxies also exist within larger structures called galaxy clusters, bound together by gravity. Within clusters, galaxies interact more frequently, exchanging gas or merging into even larger systems. The densest clusters often contain older, faint galaxies, reflecting the harsh environmental conditions, while isolated galaxies at the edges of space can retain their gas and continue forming stars for longer periods. Even galaxies, which may seem eternal, eventually face an end. As stars age and die, galaxies gradually dim, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Trillions of years from now, galaxies will no longer shine with the light of young stars. They will become vast collections of faint embers, the echoes of a once brilliant cosmos. The story of galaxies is one of constant transformation, spanning from the earliest matter clumps after the Big Bang to the silent darkness of the far future. Their lives mirror the cycles of stars, but, on a grander scale, shape not just themselves but the universe as a whole. Every galaxy we see today carries the memory of countless births, deaths, and collisions, a record written in the stars that illuminate the night sky. When we imagine galaxies, we often picture vibrant, luminous spirals, with bright arms teeming with young star clusters and nurseries of new suns. Yet not all galaxies remain this way forever. Some familiar spiral structures fall silent, ceasing to form new stars. These are known as dead disk galaxies, vast systems that no longer produce stellar offspring. Their once active lives leave behind only a faint outline of what they once were. Unlike elliptical galaxies, which appear as round, featureless blobs, dead disks retain the flat, orderly spiral shape, but their engines have cooled. They are shells of great machines, visually impressive but devoid of the energy that once animated them. At the heart of this transformation lies the raw material of stars, gas, and dust. Star formation relies on cold hydrogen clouds that collapse under their own weight, ignite fusion, and birth new suns. In active spiral galaxies, these clouds are scattered throughout the disk, creating a vibrant network of star birth and death. In dead disk galaxies, the supply is cut off. Generations of stars, either blown away by strong winds or trapped in regions too hot and stable to collapse, have exhausted the available gas. The galaxy retains its shape but has lost its spark. For astronomers, dead disk galaxies challenge long-held assumptions. Spiral structures were traditionally associated with activity and youth, while ellipticals were linked to old quiet populations. These gas-deprived spirals blur the line, showing that galactic evolution is not a simple path from active spirals to dormant ellipticals. Instead, galaxies can stop, transform, or freeze in unexpected ways. Studying these silent disks provides insight into the processes that govern galactic death. Many appear to have lost their star-forming gas long ago, suggesting dramatic and lasting events caused their dormancy. Some may have interacted with other galaxies or experienced the gravitational pull of massive clusters. In dense environments, galaxies can be stripped of gas through a process called ram pressure stripping, leaving only stars behind. In other cases, dead disk galaxies owe their silence to internal forces. Supermassive black holes at their centers can release enormous energy as matter falls in heating, surrounding gas and preventing it from forming new stars. Over time, this can starve a galaxy from the inside, leaving behind a fossil of what was once a vibrant system. The spiral arms are illuminated only by the fading light of ancient stars. Dead disk galaxies are both beautiful and melancholic. Their older, cooler stars give them a reddish hue. Without the bright blue light of young stars or the glow of stellar nurseries, their arms appear dim and almost ghostly. Observing them is like looking at the skeleton of a once lively giant. Yet, through their stillness, they tell a powerful story about the universe's constant cycles of energy and change. Dead disk galaxies also offer clues about the fate of systems like our own. The Milky Way is still active, its spiral arms hosting the birth of new stars. The universe is filled with stars that have illuminated the cosmos for billions of years, shaping the very fabric of space with their radiant brilliance. Yet, as with all beginnings, there must be an end. Every star, every galaxy, no matter how massive, will eventually dim and fade, reaching the conclusion of their life cycles. Scattered across the cosmos are these celestial graveyards, silent witnesses to the passage of time and the inevitable collapse of stars that once lit the night sky. But can life persist in a universe whose energy is gradually depleting? And what does this mean for the future of everything we know? Join us on a journey through the remnants of the cosmos. In galactic cemeteries, where the last whispers of stars tell the story of the universe's fading chapters, the birth of a star begins within a nebula, vast cloud of gas and dust swirling in the cold, infinite expanse of space. These clouds, often stretching for millions of light-years, may appear still, but they carry immense potential for transformation. A star forms when a region of this cloud collapses under its own gravity. As gas and dust particles converge, they heat up, gradually becoming denser. Initially, the gases cool and disperse, but gravitational attraction causes matter to accumulate, generating significant heat in the process, of phenomenon known as gravitational contraction. When enough mass gathers, the pressure at the cloud center rises dramatically, and temperatures soar to millions of degrees. At the heart, a protostar is born, a hot, dense core that represents the earliest stage of a star's life. Though it is not yet a fully fledged star, it heralds the emergence of the nuclear furnace that will eventually ignite. In this phase, the protostar emits substantial energy, but fusion has not yet begun. Most of this energy comes from the gravitational compression of gas. Around it, the remaining gas and dust start forming a rotating disk. Over time, this material can coalesce into planets, moons, and other celestial objects. As the protostar heats up, it reaches a critical point. The temperature and pressure at its core become high enough to trigger nuclear fusion. Hydrogen atoms fuse to form helium, releasing enormous amounts of energy, a process that marks the true birth of the star. Fusion powers the star, generating the heat and light that will shine for billions of years. To sustain this energy, the star maintains a delicate balance known as hydrostatic equilibrium. The inward pull of gravity is perfectly countered by the outward pressure from fusion. If this balance falters, the star can undergo dramatic transformations. The outer layers, still hot but not yet fusing, radiate energy into space, giving the star its characteristic glow. As fusion continues, the star remains in this stable phase known as the main sequence for the majority of its life, steadily burning hydrogen in its core. Stars like our Sun live for billions of years in this stage, while more massive stars burn their fuel far faster, quickly progressing through their life cycles. Massive stars often end in spectacular supernova or collapse into black holes, whereas smaller stars shed their outer layers gently, leaving behind dense white dwarfs. The protostar's strong stellar winds can clear surrounding gas and dust through a process called photoevaporation, creating space around the newborn star and allowing its energy to shine freely. Once hydrogen fusion dominates, the star enters the main sequence, the longest and most stable phase of its life. For stars like the Sun, this can last billions of years. During this time, the star's gravity and fusion-generated pressure maintain equilibrium, ensuring steady luminosity and heat that influence the surrounding cosmos. The final fate of the universe and the distant future of civilization, everything disappears. What remains is a universe of faint radiation, dispersed particles, and darkness. It does not collapse but sinks into silence. The Big Freeze is neither explosive nor violent, but it is absolute. It represents the slow death of everything stretched across trillions upon trillions of years. Another idea is the Big Rip, in which the fabric of reality tears apart violently, consuming everything. Instead of sinking into silent darkness, the universe would end in chaos, torn by runaway expansion. But possibilities don't end there. Some scientists imagine stranger cycles where the universe could be reborn. In one version, dark energy itself might change over time. If it weakens, expansion could slow, reverse, and lead to a collapse, but not a final dead end. Instead, this collapse could trigger another Big Bang, giving rise to a new universe. This repeating pattern is sometimes called the Big Bounce. In this scenario, universes could die and be reborn indefinitely, without a true beginning or end. Other theories suggest that our universe might give birth to new ones instead of ending. Earlier, we discussed the false vacuum concept, but there are also ideas focusing on the structure of spacetime itself. If spacetime is not smooth but has hidden layers or dimensions, the universe might not expand forever. Instead, it could eventually tunnel into a different state. In quantum physics, even seemingly impossible events can occur through rare fluctuations. The entire universe could undergo such a transformation. falling into a new configuration of reality. For inhabitants inside, this might seem like the sudden end of everything, but on a larger scale, it could signal the birth of something entirely new. Each of these visions carries its own weight. The Big Crunch offers a simple, symmetrical story of a return, a balance between beginning and end. The Big Freeze speaks of an infinite void where even memory cannot survive. The Big Rip depicts total destruction down to the smallest building blocks. The Big Bounce and related ideas suggest death is never truly final, offering endless cycles. Quantum models point to transformations beyond imagination, where the rules of reality might change in an instant. Which path is most likely remains unknown. Scientists study galaxy motions, the behavior of dark energy, and the deepest structures of spacetime. Yet the universe keeps its secrets. Well, timescales are vast, energies unreachable. What remains are snapshots, light patterns, faint signals, tiny changes in expansion. From these, we try to piece together the story of everything's ultimate fate. The fate of civilizations in the far future. Will civilizations adapt or perish? For any civilization surviving deep into the future, existence would mean confronting conditions far beyond anything imaginable in our short-lived era. What would intelligent beings do? The first challenge would be energy. All life and technology, as we know them, rely on power sources. Civilizations grow and thrive by harnessing the energy around them, whether from fire, fossil fuels, flowing rivers, or nuclear fusion in stars. But as stars age and burn out, the universe's great furnaces will close. The night sky of a distant future world will not sparkle with light like ours. Instead, it will be empty except for a few dimly glowing red dwarfs or cooling white dwarfs. Civilizations living in that era would need alternative energy sources. Black holes could become a solution. For trillions of years, black holes would remain some of the most energetic objects in the universe. Matter falling into them releases enormous energy, and even their slow evaporation via Hawking radiation could, in theory, be harnessed. Advanced beings could build structures to capture this energy, feeding matter into black holes to prolong the supply. Their worlds could be lit, not by starlight, but by systems powered by dying black holes. Other possibilities include exploiting the decay of matter. If protons eventually decay, releasing small amounts of energy, civilizations could gather and channel this energy. It wouldn't be much, but over cosmic timescales, spanning billions or trillions of years, even the tiniest energy could be preserved and expanded. Life could become a careful struggle against dwindling fuel, an existence where patience and efficiency matter more than expansion or growth. Adaptation might not be purely physical. In a universe where resources are scarce, civilizations could turn inward. Instead of sprawling empires across the stars, they could retreat into themselves, into digital or simulated worlds. If technologically capable, they could upload consciousness, existing as streams of information consuming minimal energy. Societies could persist entirely in thought, sustaining civilization in forms we can hardly imagine. For such beings, the outer cosmos might become irrelevant, a frozen void they no longer need to interact with. Survival would be about mastering themselves, not the universe. Of course, reaching such technological heights is not guaranteed. History shows civilizations rise and fall often, collapsing long before cosmic forces intervene. For far future entities, the question is not only how to survive in a dying universe, but whether they can endure the challenges of their own nature. The longer a civilization exists, the more likely it is to succumb to mistakes, conflicts, or self-inflicted collapse. Few would last long enough to face the ultimate cooling of the cosmos, yet some might survive. And survival would not come easy. As cosmic expansion continues, distances between remaining matter islands will grow vast. Communication across the universe will become impossible, leaving civilizations in profound isolation. If multiple civilizations survive, they may never even know of each other. Each would become the last light in its region, confined to solitude. Some might adapt by choosing to end their existence gracefully, letting their worlds fade while some energy and light remain, a form of surrender to the universe's fate. Acknowledging that nothing can withstand entropy indefinitely. Others may fight on, extending survival to the coldest moments, refusing to give up even as energy approaches zero. Some might even attempt to rewrite the rules of existence, creating new universes via quantum fluctuations or accessing dimensions beyond our own. Far future beings could carry their knowledge with them, planting the seeds of civilization in a new cosmos. In this sense, adaptation means not merely living in a dying universe, but leaving it entirely, sowing the foundations of new realities. For us, 1,000 years feels long. For the universe, 1,000,000,000,000 years passes in an instant. Civilizations surviving so long would measure their existence in epochs beyond comprehension. Adapting to such an environment means planning for timescales far exceeding the current age of our universe. The patience, wisdom, and resilience required are beyond anything imaginable. These beings would think and act at a pace entirely alien to USA universe, slowly advancing toward silence. Yet we can wonder, can meaning survive? Civilizations might adapt physically, finding ways to sustain energy flows and life. But in a universe growing colder and darker, what could guide them? Our civilizations depend on stories of growth, discovery, hope, and dreams. In a cosmos where nothing new is possible, where all stars have faded, does hope vanish on its own? Or do civilizations find new meaning in resisting the night? Perhaps survival is not about living forever, but living long enough to create something lasting. Civilizations might adapt as long as possible, leaving traces, structures, signals, or entirely new universes behind. Their legacy could be woven into the fabric of reality, even if they eventually perish. In this way, the struggle against a dying universe becomes a story about leaving a mark, a final echo that says, "We were here." If you want, I can also condense this into a YouTube-friendly script under 8 to 10 minutes, keeping all the cosmic drama, survival ideas, and deep physics but more concise and gripping for viewers. Do you want me to do that? The end of time, and the fate of the universe. Time is ending, the final moments of the cosmic clock. When everything ceases, what happens to time itself? We usually think of time as the stage on which all events unfold. But what if the stage itself collapses? What would that mean for the story of the cosmos? Imagining the universe's final moments is not only about the death of matter and energy, but also about whether time itself can stop. In our daily lives, time feels fixed and reliable, seemingly separate from the things within it. We wake up, clocks tick forward, and we assume that no matter what, time will always be there, counting. Yet in physics, time is not independent. It is intertwined with space, woven into the geometry of the universe. Together, they form spacetime. And spacetime is not immutable. It bends, stretches, and evolves. This means that time itself is part of the universe's story, with a beginning linked to the Big Bang, and likely an end tied to the ultimate fate of everything. As the universe expands, time stretches along with space. The cosmic clock does not tick uniformly everywhere, nor has it always ticked at the same rate. In the early universe, time flowed through a storm of energy, particles, and rapid inflation. Later, it slowed to the calmer rhythm of galaxies and stars. Today, it ticks in a way shaped by dark energy as expansion accelerates. Looking far into the future, as galaxies drift ever further apart, one wonders, does time continue marking moments forever in an empty void, or does it run out? One way to think about this is through the heat-death scenario. In this distant vision, energy is evenly distributed, and no useful work can be done. If nothing changes, if no new events occur, what meaning does time have? Time, at its core, measures change. Without change, does time still exist, or does it become indistinguishable from nothingness? Some scientists argue that even if time mathematically persists in such a universe, it loses practical meaning. The universe would end not with a bang, but by quietly fading into timeless, ness. Yet deeper possibilities exist. In physics, time is not only a concept of change, but also a dimension tied to the structure of spacetime. If space itself stretches infinitely under the influence of dark energy, time must also stretch. In this case, the cosmic clock would continue forever, but so elongated that the interval between one moment and the next could exceed comprehension. In a vast, accelerating emptiness, time could persist, but its reality would appear ghostly, as if thinned almost to non-existence. On the other hand, if the universe does not expand forever and meets a catastrophic end, time may not stretch infinitely. A big rip tearing galaxies, stars, atoms, and even spacetime itself would shatter the fabric of time. The cosmic clock would not just stop, it would vanish, leaving no framework in which before or after could exist. In this case, the last moment of time would be an absolute limit, beyond which there is nothing, not even the void we imagine. Another possibility lies in vacuum decay. If the vacuum is not perfectly stable, it could one day collapse, creating a bubble of new physics where the rules of reality, including the structure of time, are rewritten. If this occurs, our universe's timeline would be abruptly erased. The final ticks of the cosmic clock would be swallowed, and time as we know it would cease. Even more speculative is the idea that time is not fundamental. Some physicists suggest that time could emerge from deeper physical laws. According to this view, time is not a basic component of the universe, but arises from the interactions of matter and energy. If those interactions vanish, if the universe reaches maximum entropy, time could dissolve. The universe would then lack not only stars and galaxies, but the flow that carried them through existence. Our perception of time is built from memory and anticipation. We recall what has happened and imagine what will come. If the universe reaches a state with no events where new moments are indistinguishable, the difference between now and then vanishes. For a conscious observer, this would feel like an infinite present, with no changes to mark the passage of moments. This is not the end of time itself, but the loss of its meaning. Some thinkers speculate on what could exist beyond the end of time. It is difficult to imagine, because every thought we have relies on the concept of progressing time. Visualizing existence without time is like trying to see without space. It seems impossible. Yet if time is part of the structure of the universe, and that structure dissolves, time could dissolve as well. In that case, there is no beyond. The story ends not because something new arises, but because no framework remains in which anything could occur. Still, cycles remain a possibility. Some cosmological theories propose that time may not end permanently but could reset. In bouncing universe models, the end of one cosmic timeline might trigger the beginning of another. Time collapses and then restarts with a new arrow pointing forward. If this is the case, what seems like the end of time might be only the end of one version, awaiting another to begin. How time ends remains a profound mystery in cosmology. What we do know is that time is not guaranteed. It is fragile, dependent on the physics of space and energy, and intertwined with the fate of the cosmos. Thinking about the final ticks of the cosmic clock pushes the imagination to its limits, confronting possibilities stranger than any void. The eraser of time leaves behind not an emptiness but a total nothingness beyond any word, thought, or measure. Quantum resurrection and new universes. Could the universe be revived? Could quantum chance give life to a cosmos that has cooled and become inert? If the right kind of fluctuation occurs, it could gather enough energy to trigger a miniature Big Bang, igniting a new expansion. In this case, a region of space could suddenly inflate into a brand new universe. Our universe would not truly end. Quantum mechanics might, by chance, give rise to another. This idea is sometimes associated with eternal inflation. In this view, our universe may be just one bubble among many. The Big Bang may not be the ultimate beginning, but a local event, a spark within a larger reality. If so, the end of our universe is not a final wall, but a doorway to the possibility of new universes. Quantum fluctuations could ensure that creation never fully stops, even if one universe dissolves into nothingness. A stranger aspect of this idea involves local events rather than entire universes. Some physicists speculate about self-aware structures, sometimes called Boltzmann brains, that could emerge randomly from quantum chaos. The idea is that, given enough time in a universe approaching heat death, chance fluctuations could briefly produce complex structures resembling conscious minds or even patterns of thought. These brains would not persist long, vanishing almost as quickly as they appeared. Yet, in the ultimate silence of the cosmos, they represent a shocking possibility. Sparks of isolated awareness, independent of stars, planets, or galaxies. If chance can create such complexity, then the resurrection of an entire universe is also possible. This would not be a return of the lost, but the emergence of something new from randomness. Just as the Big Bang was a sudden, inexplicable release of energy, a future fluctuation could trigger another moment of expansion, a reset of time, another chance for creation. The challenge is scale. Quantum fluctuations are common but tiny, always occurring in empty space. What is required is a colossal fluctuation capable of triggering inflation and building a new universe. The probability of such an event is unimaginably low. Yet the universe has time, trillions upon trillions of years, beyond human comprehension, so even the most unlikely events can eventually occur. What seems impossible on human timescales becomes inevitable over cosmic timescales. If such a new universe arises, what would it look like? Would it carry memories of the old, or be entirely new? Most theories favor the latter. The birth of a universe through a quantum fluctuation erases the details of the previous one. Physical constants may differ, dimensions may be unlike ours, and laws may be strange. In this sense, the reborn universe is not ours, but a foreign reality arising from the ashes of the old. Whether such a rebirth could be observed is also questionable. A fluctuation creating a new bubble universe could be entirely disconnected from ours. To us, our universe might seem to end with heat death, without any visible resurrection. The new reality would bloom in isolation, hidden from the eyes that perceive us. If universes can arise from fluctuations, perhaps reality as a whole is an endless cycle of birth and death. Each universe follows its course, cools, and dies, while another exists somewhere in the quantum sea. This cycle could continue forever, without requiring a beginning or an end. Our universe would then be only a link in an infinite story, a moment in a chain extending beyond time. This image is comforting, suggesting that creation never truly stops. Even after our universe dies, reality itself continues. Yet, it is also unsettling, implying that our universe is not special, just one of countless experiments realized by chance. Quantum resurrection is not a return of the lost, it is the infinite possibility of something new, arising from randomness. Alternative endings, and the big freeze. When humans first imagined the end of the universe, the idea of a big crunch seemed natural. If the universe began with a bang, perhaps it would end with a collapse. The reasoning was simple. Gravity pulls everything inward. If there were enough matter and energy, expansion would slow, stop, and reverse. Galaxies would converge. The far future of the universe and dark energy. Light from a distant galaxy takes billions of years to reach us. However, as dark energy expands space, it stretches the light, shifting it toward longer wavelengths. This redshift makes distant galaxies appear dimmer and redder as they recede. Eventually, galaxies will redshift so much that their light becomes invisible, and the night sky will grow darker and emptier with each passing century. Stars will continue to shine for a while, but the magnificent view of a living and expanding cosmos will fade. What makes dark energy even more perplexing is that its strength does not diminish as the universe expands. Ordinary matter grows as the same number of particles spreads over a larger volume. Radiation thins even faster as its energy stretches with expansion. Dark energy, however, remains constant. No matter how large the universe grows, its effect per unit volume stays the same. This property shows that it is not matter in the usual sense, but something linked to the very nature of space. Some scientists suggest that dark energy may be the energy of the vacuum itself, a fundamental energy present even in empty space. Others imagine it as a new type of field permeating the cosmos, affecting how gravity behaves on the largest scales. So far, no experiment on Earth has directly measured it. We observe its fingerprints only in galaxy motions and the patterns left by the cosmic microwave background. If dark energy continues to behave as it does today, the universe will accelerate forever. More extreme possibilities exist. If dark energy strengthens over time, it could rip apart galaxies, solar systems, and even atoms, a scenario called the Big Rip. Conversely, if dark energy weakens or changes, the universe could slow down or even reverse, collapsing again in a final crunch. For now, the best evidence points to perpetual acceleration. Galaxies will recede until each becomes an isolated island of stars surrounded by darkness. Beyond their horizons, the universe will become unreachable, locked by relentless expansion. In this way, dark energy shapes not only the present but the distant fate of everything, expanding not just space but the very meaning of time, creating a cosmos that is vast yet fleeting, filled with countless galaxies but destined to hide them from view. A cold and empty universe, life beyond thermal death. Could anything exist in any form in such a universe? If life is defined by continuity, perhaps even its quietest and most fragile forms could extend far beyond what we consider an end. To imagine such a future, it helps to consider what life requires. All life we know depends on flows of energy. On Earth, plants capture energy from the sun. Animals feed indirectly on this energy. And even deep ocean bacteria rely on chemical energy to sustain themselves. Energy is the spark that allows order to resist the natural pull of disorder. In the far future, when the universe reaches heat death, finding this spark will be nearly impossible. Energy will be so evenly distributed that no natural flows will exist. Without gradients or temperature differences, there is no way to exert force, yet some speculate whether the faint residual energy vibrations might somehow allow a form of activity to persist. Physicists sometimes imagine extremely slow processes, civilizations, or entities that operate over timescales so vast they are almost imperceptible to us. Imagine a mind thinking once every trillion years, patiently monitoring tiny changes in background radiation or rare particle collisions. To us, such life would appear frozen, but from its perspective, thought, memory, and perhaps awareness could still exist. Others note that the structure of energy itself might emerge from the essence of spacetime. Quantum mechanics implies that empty space is not truly empty. Small fluctuations constantly produce virtual particles entering and leaving existence. Today, these fluctuations are negligible. In the distant future, when all other energy sources are gone, these might be the only usable energy. Advanced life, if it survives that long, might learn to harness them, finding a way to spark activity in a stagnant sea. Some scientists even consider whether information itself could act as a form of life in the far future. If matter is gone and energy useless, perhaps patterns of information stored in quantum fields could persist. After all, life can be defined as information organized to resist decay. Could these informational patterns continue even when the physical carriers are gone? This is highly speculative, yet it reflects the human urge to imagine survival against absolute stillness. The universe's heat death is expected no earlier than 10,100 years, a number beyond comprehension. By then, not only stars and galaxies, but even protons will have decayed, leaving only radiation and occasional drifting particles in endless darkness. Any life or lifelike entity existing then would be almost unrecognizable to us, appearing as rare, scattered pulses of activity in a silent ocean. Philosophers sometimes describe such imagined existence as a ghostly life, persisting in ways beyond our current understanding of life's meaning. If such entities could think, would they consider themselves alive? Or would they be mere echoes of a universe that once hosted stars, galaxies, and worlds full of wonders? Perhaps the laws of physics as we know them do not permit permanence once energy reaches equilibrium. In that case, life's story would be a brief chapter in the broader history of the cosmos, a flame that shines brightly for a time, then fades, leaving only darkness. For some, this is unsettling. For others, poetic, a reminder of the value of the present. Imagination does not stop there. Some theorists wonder if new universes could emerge even from the ashes of heat death. If quantum fluctuations are real, perhaps one could spawn a larger bubble of energy, expanding and igniting a new Big Bang. In this sense, the universe may never truly die. Instead, countless new universes, each with its own story, could arise. If so, life or something like it might always find a new foundation to take root. Science provides outlines, probabilities, and mathematical models, but it cannot yet tell us exactly what will happen. What is clear is that life as we know it cannot continue in such a universe. Whether an almost unrecognizable form of existence might emerge remains an open question, reflecting not just the limits of physics but the infinite reach of human imagination. Perhaps, in the shadows of nothingness, something unexpected awaits, something that could transform the end into another beginning. The decay of space seems like a silent backdrop in which everything unfolds. Stars burn, galaxies drift, black holes devour, and planets orbit within the invisible fabric we call spacetime. It feels permanent, like a canvas that cannot tear, bend, or fade. Yet some physicists ask, what if this canvas is not infinite? What if space itself could decay, slowly wearing away until nothing even empty? This idea may sound strange, even unsettling, because space seems like nothingness. But in physics, nothingness is not the absence of existence. It has embedded rules, structure, and energy. Space expands, bends under gravity, and allows time to flow. Passive as it may appear, it actively shapes everything we know. If space-time itself has fragility, the universe's long-term future might not only be cold or dark, it might be fundamentally unstable. One way scientists explore this is through the idea of vacuum decay. In physics, vacuum refers to the lowest possible energy state of space. But what if the vacuum we live in is not the absolute lowest state, but only a temporary one? Imagine a ball resting in a shallow valley. It seems stable and can stay there for centuries. Yet beyond the hills, a deeper valley may exist, a more stable resting point. If the ball rolls into that valley, the state of the entire system changes. Similarly, our universe might exist in a place called a false vacuum. If this is true, space could one day collapse into a new form. A true vacuum bubble might suddenly appear in a distant region, triggered by quantum fluctuations. This bubble would expand near the speed of light, rewriting the laws of physics inside. Forces holding atoms together, the structure of time, even the very existence of matter could vanish or transform beyond recognition. There would be no warning, no escape. To an outside observer, it would be the ultimate collapse. As if the universe rewrote its own code, this highly speculative idea arises naturally from the equations of quantum field theory, the same mathematics that defined particles, energy, and the early universe. Some researchers point to the Higgs boson, discovered in 2012. As a potential hint, its measured mass suggests our vacuum could be metastable, delicately balanced between stability and collapse. If true, space-time itself carries the possibility of ultimate decay. Other scenarios consider whether cosmic expansion might weaken space-time. As dark energy drives galaxies apart, space stretches faster and faster. Could this stretching rip the very fabric, leaving behind nothingness? In this picture, acceleration never stops. Galaxies tear apart, stars disintegrate, planets shatter, and ultimately atoms are drawn into the void. What remains is not a new structure of space, but the collapse of structure itself. Even without a dramatic rupture or bubble decay, a slower thinning of spacetime remains a disturbing possibility. Like heat spreading in the heat death scenario, the fabric of space could become less dynamic, less structured, and more phantom-like over time. Trillions of years in the future, we might face a cosmos where space exists in name only, devoid of any property to sustain the flow of events. In the most extreme cases, this raises the silent death of the universe. In this sense, the universe does not die with a violent end, but through a quiet exhaustion. All the drama of creation, the fiery birth of stars, the collisions of galaxies, supernova explosions, pales in comparison to the eternal stillness that follows. If the universe is inevitably drifting toward this final frozen state, all structures we see today, from galaxies to life itself, are merely temporary patterns on a calm and motionless ocean. Some thinkers find this vision bleak. Even the greatest achievements are buried in silence. Others see beauty in the idea that we live during the universe's brief, radiant period, when stars still shine and life is still possible. Thermal death is not only an end but also a reminder of how precious the present is. Yet, some scientists wonder whether this thermal death is truly inevitable. Could unknown physics alter this picture? Could the universe return to a new beginning? Might dark energy itself change over time, rewriting the fate of all things? For now, heat death remains the most widely accepted scenario, grounded in thermodynamic laws and the gradual unfolding of entropy across the cosmos. To imagine heat is to imagine death as an endless silence. It is the ultimate grave, not of a single star or galaxy, but of everything that exists. Yet, in contemplating this, we also recognize the remarkable reality of today. The universe still shines with light. still pulses with energy, still creates wonders. The funeral may come, but for now, the cosmos still sings. Information. The universe's memory at its birth. The universe was brimming with information. Every particle, photon, and interaction carried the record of what came before. The cosmic microwave background radiation, still observable today, is a relic of the baby universe. Patterns in galaxies, the motions of stars, even isotopes in planets, all tell the story of ancient processes. The universe, in many ways, is a library written in matter and energy, and each structure contains a page of its history. Like any library, pages can deteriorate. Ink fades, and over long timescales, even the most robust records may vanish. In physics, information is more than data that is connected to the organization of matter and energy. When a star forms, its light carries information about its temperature, mass, and age. When it explodes as a supernova, it sends a final message in radiation and heavy elements. These are data fragments freely scattered across the cosmos. Black holes complicate this picture. Classically, anything falling into a black hole is lost forever, sealing its information. This paradox puzzled scientists for decades. Quantum physics suggests otherwise. Hawking radiation gradually releases information, scrambled into the universe. It is never destroyed, only transformed into faint whispers of heat. Yet, even if this information eventually leaks out, it is so disordered that it can never be reconstructed. The story it once told is effectively erased, replaced by noise too weak to interpret. As time passes, the universe trends toward equilibrium. Temperature, pressure, and energy differences fade. Entropy does not annihilate information, but it makes access increasingly difficult. Imagine a book torn into fragments and scattered in the wind. Theoretically, the information still exists, but reassembling it is impossible. The same is true for the cosmos. Over trillions of years, particles drift apart, energy spreads evenly, and records of past events fade into patterns that no longer reveal their origin. Dimensional decay. The fabric of reality, space, and time may not be permanent. Far in the future, after galaxies fade and stars collapse into ashes, the universe could face a stranger fate, dimensional decay, where the very fabric of space and time begins to unravel. Space may no longer provide directions, and atoms may not hold together because the arena in which they interact has collapsed or perhaps ceased to exist altogether. Time may lose its consistency, no longer flowing as ordered moments but fragmenting into disorder. This is not purely science fiction. String theory suggests the universe may have more dimensions than we perceive. Small, hidden dimensions could be unstable, capable of vanishing or changing. Quantum gravity proposes that space-time itself may be discrete, like pixels on a screen. If these fundamental units fracture or reorganize, the larger fabric they form could dissolve. Even the laws we consider permanent might be temporary, emerging from deeper conditions that could themselves vanish. Dimensional decay would not only erase space, but also the rules that make the universe coherent. Life or intelligence would have almost no chance of enduring. Survival presumes a framework of space and time. Without them, there is nowhere to go, and no sequence in which events can occur. Yet even then, could something emerge? When a structure collapses, its fragments sometimes create new forms. A dying star may become a neutron star. Could the collapse of space and time give rise to a new type of framework with different dimensions or laws? If so, dimensional decay might resemble a transformation, with the threads of reality rewoven into a new pattern. Whether this new cosmos could support anything resembling matter or life is unknown. Distances, time, and existence itself could be alien beyond comprehension. Dark energy and cosmic expansion. Dark energy stretches space itself, accelerating the expansion of the universe. Without it, gravity might eventually slow expansion, allowing galaxies to remain closer. Instead, dark energy ensures voids grow, and distant galaxies will eventually recede beyond our cosmic horizon, never to be seen again. For future observers, only gravitationally bound local galaxies will remain faintly visible. All evidence of a larger cosmos may vanish. Dark energy warps the perception of time. As the universe expands, its speed increases, stretching the flow of cosmic history. The farther into the future we look, the emptier and lonelier the universe appears. Regions once accessible to telescopes or signals will become forever out of reach. Space itself will not only expand but isolate galaxies, making communication and travel across the cosmos impossible. Reflection. The universe's distant future may be a silent, frozen wasteland, yet today we live in a cosmos still alive with light, energy, and wonder. The stories of stars and galaxies continue to unfold before us, a fleeting but extraordinary chapter in an inexorable cosmic tale. Even if the ultimate end is quiet, ephemeral, and beyond comprehension, the present moment remains a luminous testament to creation itself.